So now let's look at our section 4.6 on linear regression. Regression is kind of a big word, and if I just use the word regression in like everyday language, it doesn't seem like it has the same meaning that we're using it for here. Okay, and that's just from, I guess, history, right? So what happens is there's a history to when linear regression sort of came about, and some people who made it popular were doing some specific applications, right? And I think that they were looking at like um, plants and genetic genes and how they would regress back to earlier traits. Okay, and so we sort of publishing using some certain terminology, and when the context changed, they kept the same term. So regression here doesn't have the same meaning as it does in regular English. Okay, and we have it gets worse because we throw like this least squares thing in the front, and we'll talk about why we do that. All right, so when we're working with real life data, um, our points don't always fall out neatly on a line. Okay, um, so let's look at some examples of what data might look like. Suppose my explanatory variable is like weight of a car, my response variable is highway miles per gallon, and I get a bunch of data points. I can't draw one single line that connects all of these points. Okay, and we have other examples here too, and this is just looking at data that we would collect. They don't all fall neatly on a line, but I might still want to model these with a line. And the idea is that if I look at this, it's not that they fit all perfectly on a line, but I could probably draw a line that gives me an idea for the general trend or pattern that's going on. That one's not very good. Okay. And the thicker the line I draw, the better, right? But really what we're doing is we want a real line, a regular, one-dimensional line. And we want to use that to sort of model the pattern behind the data. So we recognize that it's not going to be a perfect fit, but we can use it to maybe make predictions in the future and also to tell us about what sort of pattern that we have going on. For example, with this first one, I can see that as your weight of the car increases, it looks like your mileage, your highway mileage, is going down, which hopefully makes sense. That hopefully lines up with your real world experience, right? Smaller, lighter cars typically get better mileage than big, heavy cars. Okay. But we also know that, like, if I look at different cars, the weight isn't like the only factor. Okay. So I know that, from one model to another, maybe one is more aerodynamic than another. So I could have cars that are the same weight or close to the same weight, and one has a much better mileage than the other. Maybe it's more aerodynamic or has a more efficient engine. Okay. There's other things that can come into play, but I can still get sort of a general pattern, right? I can say, all right, as you get a heavier car, the mileage is going to be worse, right? So that's what we want to do here. We want to look at modeling real data, and so we know that a line isn't going to fit perfectly. We don't have all the points lining up neatly. Okay, so if I ask this first question, can I just connect the dots and get a line? The answer to that is no. All right. And it gets worse. If I look at these graphs, are these graphs a function? Well, if I try the vertical line test, if this is a point on the graph and this is a point on the graph, I think those are the same x value. And if I have the same x value and I have two different y's, then that's not a function. Okay, it's very clear on the second and third graphs, right? I can definitely find, 2 points with different y values, same x value. So the first one's maybe a maybe. I can't tell if this one is a little bit over or not. Second two, I think, are definitely no's. So are all of the above graphs functions? No, they don't pass the vertical. I don't have a nice line drawn through them. But remember, when we were looking at functions, we didn't have to have a nice line drawn through. We even just looked at tables. And if you had two points that had the same x value and different y values, that was enough to not be a function. Okay, so we could say these don't pass the vertical line test, or there are points with the same x but different y's. Okay. So now we figure out, all right, these aren't functions. They're definitely not all in a line. So that seems very problematic. How do I fit a line to this, right? I could look at this, and I sort of drew in lines, roughly. They're not exactly lines because they're nice and thick here, but we can look at this and say there is sort of a pattern to this data. It looks like I could draw a line through it. The problem is that you can draw more than one line through it, right? So, you know, I drew this line in blue. What if somebody else comes over and says, I think that, oops, overlapping exactly. But let's suppose somebody comes by and says, I like this line better. How do we know which one fits best? Well, we have to be careful about that, right? So here's an example. Which of the following songs is the best song, right? Royals by Lorde, Roar by Katy Perry, Wrecking Ball by Miley Cyrus, Dark Horse by Katy Perry. And if I asked, you know, everyone to answer which is the best song out of these four, I think that you could guess that we wouldn't all get the same answer, right? And why is that? What's wrong with trying to find an answer to this question? When we ask for what is the best song, we may not all be using the exact same criteria for what is best. Okay, so we don't all mean the same thing, or another way to think about it is we might be using different criteria to judge these songs. Okay, that doesn't mean that one person is right and one person is wrong, although, you know, if you're sitting around at a party having a beer, then you can certainly argue that. That might make for an interesting conversation. Okay. But the problem is that, you know, if you're not all, you know, if you're just saying, well, this one sounds the best to me, well, you know, and I say, well, this one sounds the best to me, well, that's still different criteria, right? Even which one sounds the best isn't right. All right, let's look at the same list of songs and say, okay, which of the following songs is by Katy Perry and has a title that starts with an R? That's one that I think that we can all agree on, right? We could say there is one song on this list that meets those criteria. Okay, so there we can be clear and we can all agree. So when we talk about a best fit, what we need to do is we need to all have a very specific set of criteria that we're judging on so that we all arrive at the same conclusion. Okay, at least in math, that's what we want to do because we want to have the same result. Okay, when we're talking about, you know, at a party, what's your favorite music, then maybe we don't care that we all land at the same spot. That's not a big deal. But in a math class, we want to make sure that we all land on the exact same line for which one is the best fit line. Okay, so what we're going to do is we're going to come up with two criteria for what makes a line the best fit out of all of the possible lines that I could draw. Okay, so here's the criteria that we're going to use. And because best fit, if I changed my criteria, I would have a different one. We want to label what type of line we're drawing based on the criteria that we're doing. Okay, so these two criteria that we're going to come up with will result in something called a least squares regression line. So we label it, we talk about this as being least squares because that's going to be part of the criteria that we use. And so that sort of lets people know this is how we chose, this is the judgment or criteria that we use to pick our least squares line. Okay, so here's how we do our criteria. What we're going to do is first pick you can think of it as average point. Pick the point where I average all the x's, and that's my x value, and average all the y's, and that's my y value. Okay, so this x bar is the average of all x's, and this y bar is the average of all the y values. Okay, and what we do is our first criteria is that the best fit line has to pass through this point. Okay. The way to think about how we're picking these criteria, in order to draw a line, I really need two pieces of information. I need a starting point, and then I need a direction. So we're going to pick this as a starting point, and we're just averaging all of the x's and y's that we have, and that seems like a pretty reasonable way to start. Okay. The next piece of the criteria is to pick the direction. Okay. Now, what I want to do is first show you how we can go about getting this this average point. So here's what I'm going to do. We're going to pick this set of data. Okay, weight of a car and highway mileage. Okay, and I'm going to enter this data into my calculator. We're going to use this for a couple examples in this section, so we're just going to keep it. On the notes, it says put this in L5 and L6, and the reason is because we're going to use this in more than one example, and that way we don't end up erasing it if we go do a different problem. So I'm just going to put these over here in L5 and L6. So I'm going to put my weight of the car, so 29.48, 35.36, right, and so on. I'm just going to fill all of these out. Okay, and then over here in L6, I'm going to put the highway miles per gallon, making sure that they line up. So this 2782, right, corresponds to a 20, and in my data, the 2782, right, corresponds to a 20. Okay, so just making sure that things line up as I go. So 20, 14, 16, and so on. Okay, what I can do now is to compute things like this average XY, I can go over to stat and calculate. In statistics, we always had just one variable at a time that we were working with, so I'd use one variable statistics. Here I have an X variable and a Y variable, so I go to two variable stats. Okay. And because I put my X list in L5, I need to hit second and hit 5 to get L5, and my Y list is L6. And I don't want a frequency list here. I hit calculate, and here it tells me an X bar, and if I scroll down, it tells me a Y bar. Okay. So that's how we can find this average point, right? So 3,208.5 for our X value average. And the Y bar is 20.1, so 20.1 is going to be my Y value. Okay, now, how many different lines can I have that goes through that point? Right? Well, the idea is, I could pick a different direction. There's infinitely many lines that I could pick, right? And what we want to do is we want to say, all right, I want to find which one fits the best. So we want to imagine, if I take this point on my graph, So let me just draw a quick graph over here. Okay, suppose I have my average point here. What we want to do is imagine that we draw a bunch of possible lines through that point. Okay, and we want to find out which one fits the best. And again, we need a criteria for which one fits the best. Okay, so let's just back up a little bit and be careful about how we're going to pick this criteria. So we're going to talk about something called residual, and then we'll come back to saying, how does that help us pick this best fit one? Residual is going to be the gap between our line and a point, right? So if I look at my graph and I say, here's a point, okay, it's this far above the line, or here's a point, it's this far below the line, those are going to be residuals, okay? Right. So the residual is just the difference between the actual data point and the point with the same x value on my line. Or another way to think about that is the residual is the difference between my observed y, which is the real data point, and the predicted y, which would be the point on my line. Okay. So over here, I would have a positive residual. Over here, I would have a negative residual. Because here, if I subtract, my observed y is a bigger number than the y value on my line, so when I subtract, it'll be positive. If I subtract in the same order, right, if I have this point below the line and I subtract a bigger number, I'm going to get a negative. Okay, so a positive residual means the y value minus y hat, which is the point on the line, is positive, which means y is bigger than y hat. Okay, so the observed value of y is larger than the predicted value of y. Okay. For a negative residual, the observed value of y is smaller than the predicted value. Okay. So what we can do is we're going to look at the residuals, and it turns out that for any line you draw, if I add up all the residuals, I get 0. So that's not very helpful. What we're going to do, though, is we're going to square the residuals. Okay. And this does two things for us. First of all, that means that I don't have any negatives, so they can't all add up to 0. The second thing it does for us is that it's going to emphasize big gaps. When I'm trying to fit a line, and if I'm looking back at this, and I say, okay, these points are really close, okay, I'd say that that's a pretty good fit. I know that I can't fit them all perfectly. A lot of small gaps is fine, but I would say these big gaps, that's what I have to worry about. And if you drew another line that fit more of the points well, but fit this one point a lot worse, I would say, well, if I'm looking at predicting values, I've got a much bigger margin of error going on here, so I don't think this line really fits as well. It's not going to be as good at predicting things. So it might fit some of these other points that already had a small residual. Maybe it fits some of them better, but if it makes some of these big ones worse, then I'm not really making forward progress. So the idea is if I square these residuals, what I'm doing is I'm emphasizing a big gap because I don't want a lot of big gaps and I don't want my gaps to get too big. Okay, so that's going to be more important than a lot of small gaps. Okay, so that's why the squaring is maybe a good idea. Okay, so the idea is now, getting back to the idea of drawing a best fit line, we start at our fixed point, and you can think about tilting our line back and forth or looking at all those infinitely many lines until we find the one where the sum of the squares of the residuals is as small as possible. Okay, that's the idea of what we're going to do. Okay. So we have two criteria now. Our best fitting line using the least squares principle is 1, it passes through that average point, and 2, it makes these, right, this is the sum of the residuals, actually sum of squared residuals, as small as possible. Okay. And there is like formulas for computing this, but those are built into our calculator, so we're going to have our calculator do all that hard work for us. Okay. And the idea isn't that it actually tries all of these lines out and then computes the residuals. There's, somebody was clever enough to figure out this is how to compute the line that will end up having the smallest sum of least squares residuals. Okay. And so it just uses that. But even that formula is a little bit complicated, so we're just going to let our calculator handle it. Okay. So here's how we can do that on my calculator. Remember that I have all of my data in here, and I put it in L5 and L6. Okay, so from my home screen, what I can do is I can hit Stat. I've already entered the data, so you would press 1 to enter the data. We've already done that. So now I go over to Calculate, and instead of calculating 1 or 2 variable statistics, I go down to this LinReg, stands for linear regression. Okay, so I click on that. My X list is L5, my Y list is L6, and I can just hit Calculate. Okay, and what this does is it's going to tell me y equals ax plus b. So it's telling me, okay, a is the slope and b is the intercept, and then it writes out the number for slope and the number for the intercept, okay, using all the decimals. So if I wanted to write this equation of the best fit line, now I can just do that. Okay, so find that linear regression equation on my calculator. So I'm cheating a little bit. I have that screen over here. So I could say, okay, y equals negative 0.00456x plus 34.7359. Okay, and I rounded to 4, I guess in this place, 5 decimal places. Okay, you could use all the decimal places. When you're doing this on your homework, it'll tell you how many places to round to. Okay, so that's how we get an equation. All right, now we have to be a little bit careful. If I go back and I think about what we're talking about, we're looking at the weight of a car and we're looking at the highway miles per gallons. So once I have this equation of a line, I can make a prediction. You could tell me a weight of a car and I could predict the highway mile per gallons. What we want to do is make sure that we're being reasonable with our predictions. So if I look at these weights of cars, okay, these are all like the weight of like a normal car. If I try to use the linear model that takes all of these normal sized cars and I want to use it to predict the highway mile per gallon of maybe like an 18-wheeler semi-truck, that's probably not going to be very reliable data. Or if I go the other direction and I say, okay, somebody's got a motorcycle, let's predict the highway mile per gallon for that, and that's much lighter than all of these cars that we picked, well, I would say, well, we didn't use that kind of data to make our model, so it doesn't make sense to use our model to make those predictions. Okay, so we want to make sure that we're using our model reasonably, and that's where this next piece comes in. So the restricted domain is going to say we only want to use x values that look like the x values that we used to come up with our equation. So our restricted domain is just going to be make sure you stick to x values that are in the same range as the x values that we started with. Okay, so we're going to use the smallest and biggest x values as sort of boundaries. So when I look back up at my data here, I think that the biggest x value is this 4,367. And I believe that the smallest x value is this 2,526, but I'm going to scan across again and make sure. Okay, so when I write my restricted domain, I want all of my x values to be in between these two. I want them to be smaller than 4,367, and I want them to be bigger than 2,526 so that I can feel like I'm being reasonable with how I'm applying my model. Okay. What does the model predict for highway fuel efficiency for a car that weighs 2,948 pounds? Well, the weight of a car is my input variable. I'm going to think of that like x. So what this is saying is compute y for x equals 2948. And I can say 2948 is in my restricted domain, right? It's in the right range of values. So now I can just plug it into my equation for a line. Let's say y, okay, y equals negative 0.00456 times 2948 plus 34.7359. Okay. And I'm going to use my calculator, of course, to do that. Okay. And I get 21.29302. Okay. My y values have a units of miles per gallon, so I can put that in there, mpg. Okay. Now let's compute the residual associated with that point, right? Because if I look back at my original data, I have a car that weighs exactly that amount, right? This 2948 wasn't picked at random. That's the first car on our list of data. So when x is 2948, the observed value of y, right, the car that we actually measured was 23. Okay, the predicted value of y comes from the equation of the line, and that was 21.29302. Okay, so maybe I'm just going to make a note over here to this on the side. The observed y comes from the data set. Okay, the predicted y comes from the model or the equation. Okay. So my residual is, and this is written in function notation, y when x is 2948 minus y hat, which is the one on my model, right? My predicted line, when x is 2948. So I take my observed y minus my predicted y, right? The observed y we just said was 23 minus the predicted y, which is 21.29302. And when I subtract those, I get 1.7 and change. Okay. And what I want to do is interpret that in context. So what I want to do is write a sentence, right? When you see the word interpret, that means write a sentence. Okay. So let's interpret this in context. Our observed y, so somebody's particular car, got 23 miles to the gallon, which was 1.7 miles to the gallon more than we predicted. Okay, so the car that weighs 2,948 pounds gets 1.70698 miles per gallon more than our model predicts. Okay. You could have other interpretations. You can also think of our model as being like a moving average. It's like the average mile per gallon for cars that weigh that particular amount. So another way to interpret this is you could say that it gets 1.7 miles per gallon more than average. All right, let's look at the list of residuals on our calculator and round each value to the nearest tenth. Okay, so what I want to do is I want to have my calculator compute a bunch of residuals for me. Okay, and it kind of already had to do that in order to create my best fitting line that we got, right? When I hit this linear regression thing, okay, in order to compute these values, it had to compute those residuals internally, okay, and you know, we can call those up. So there's two ways to do this. You could compute each one of these manually, right? So we just did this first one by hand, right? And I got this 1.7 if I rounded to one decimal place. So I know that my first residual is, if I round to one decimal place, 1.7. Okay. But I don't want to do that by hand for all of the rest of them. Okay. So what we're going to do is we're going to go through some steps on your calculator to look at all of these residuals. And let me see if I can hold that on there. Give me 1 second here. Okay, sorry. Here's where your calculator stores the residuals. If I look above the stat button, there's list. Okay, this gives me the list that I have in my calculator: L1, L2, 3, 4, 5, and 6, and it also has the residuals on there. Okay, so you can hit that, and that'll give you all of your residuals. This is kind of a cumbersome way to look at your residuals. So what I want to do is maybe make that as a nice neat table in my calculator. So what I'm going to do is I say, okay, here's my X values, here's my Y values, and what I'm going to do is just make another column with my residuals. Well, let me go, yeah, let me go over. So we're going to go over one more. And what I want to do is let me go back and make sure that we're doing this step by step here. So we hit stat, edit, and this is where we put in our data, our X data and our Y data. So I'm just going to go over one more, and it doesn't let me when I'm down here, but if I go up so that I'm selecting the names of the lists, then it will let me go over to create another list. And it says, please give a name for this list. So I'm going to hit enter, but I'm not going to create a name. I'm going to enter in that residual list that it already has. So when it asks me for the name, I'm going to hit second and hit list, and I go down to residuals. Okay, that's the list that I want here, and I hit enter, and that will give me all of my residuals. Okay, so rounding to one decimal place, I can see I got, okay, there's my 1.7, 0.4, 0.1, and so on. So I can just write them all down. Okay, notice that some of them are negative, right? So this next one is negative 2.0, negative 3.6. Okay, and I have 1.2, negative 1.7. Okay, negative 0.2, 2.4, and 1.7. Okay. What will the sum of these residuals be, right? So if I add these up, 0.7 plus 0.4, if you've been paying attention, you might know even without having to add them up. Then when I add up all these residuals, I'll always get exactly 0. Okay. So the sum of these residuals is 0. Okay. Should the model be used to predict highway fuel efficiency for a car that weighs 4,500 pounds? To answer that question, to answer this, what I want to do is go back and say, up here, my restricted domain said stay between 2,526 and 4,367. 4,500 is too much. So what we can do is we can say, no, it is outside our restricted domain. Okay. Or another way to answer that is you could say, no, this car is heavier than anything in our data that we used to make the model, and so it wouldn't be appropriate to use our model to make a prediction for it. Okay. It's heavier than any of the cars in our sample. All right. All right. So let's go. Let's answer a few more questions. Wait a minute. I think this is the exact same. Sorry, that was the same question. Okay, so let's jump down here and talk about slope and y-intercept. So we computed the slope and we computed the y-intercept for our model here. Okay, the slope is the number on the x. So even though it doesn't write it as mx plus b, it writes it as ax plus b. Don't worry about that. The number on the x is the slope. So our slope, we said, was negative 0.00456. What we want to do is make sure that we can interpret what that means, okay? That we can go between a number and, a sentence. So the way to think about slope is going to be the change in y for one additional x. So what we can do is say, in this case, our x value is a pound of car. So for every additional pound of vehicle weight, okay, the model predicts that the y value, which is highway miles per gallon, will decrease, because it's negative, by 0.00456 mpg on average. Okay, so we recognize that our model isn't going to exactly fit all of the data points. It's giving us a general trend or an average for how the cars behave. Okay. The y-intercept is the y value when x is 0. Okay. In this case, my y-intercept is 34 point, we'll just write 74 because I'm out of space here. So what I could do, interpret that, was I could say, well, the y value is miles per gallon and the x value is the weight of the car. So I could say that our model predicts that a car that weighs 0 pounds will get 34.74 mpg. Okay, which is completely meaningless, right? A car that weighs 0 pounds there's no car there, right? So in this particular context, it doesn't make sense to talk about a y-intercept. Okay. Right. So for some examples that we have, the y-intercept doesn't make sense. And that's fine. We want to say that. We don't want to say that, we're going to get 34.74 miles per gallon when you don't have a car. That doesn't make any sense at all. Okay. And in general, if your y-intercept is not in your restricted domain, then we can just forget about it, right? Because we don't care. That's not, the model doesn't apply to those outside that range. Okay. It always makes sense to talk about slope, so we can always interpret slope. Okay. We only interpret the y-intercept if it's in our restricted domain. Okay. All right, I think that will do it.